Okay, so I think I can start my talk. So I will chair myself. So and the last speaker, Shiping Liu from USTC. So I will talking about something already mentioned in the last talk. It's called it's about the discrete nodal domains. But this talk is still in the linear world for the linear Laplacians, but still a bit different from the classical graph Laplacian. So actually we will try to deal with a general symmetric matrices. So we know for graph Laplacian, if you look at the matrix form, it is a symmetric matrix, but with the special property that all the off-diagonal entries are non-positive. But we won't get rid of this restriction, so just try to study arbitrary symmetric matrices. It turns out that for those matrices, a proper tool to deal with is the so-called signed graphs. So it's a normal graph with some additional signature structure, which I will first discuss in the beginning of my talk. So I will first explain the signed graphs, then I come back to these nodal domain theorems for arbitrary symmetric matrices. Okay, maybe let me start with some explanation about spaces. So we know that Newton and Leibniz actually have different opinions about space. For Leibniz, space simply encodes relations between objects. So I think during the developing of networks and computers, it seems like this opinion is more and more correct. For example, we have a lot of networks nowadays, and we have so you can think about it. It has a space. The objects are just these discrete elements, and the relations is represented by edges. So mathematically, this is encoded by a graph. So what is a signed graph? A signed graph is like you try to make more different types of relations between discrete objects. So for graphs, either two pair of vertices have relation or have no relation. Or you can see that between any two pairs of vertices in a graph, you only have two types of relations. So we try to increase these types of relations from 2 to 3 by this signature structure. So what is a signed graph? A signed graph is a normal graph with a signature map. So I assign to each edge a +1 or -1. So this concept, this structure is actually very simple. So now it's like between any two vertices, you have 3 types of relations. Either there's no edge, or there exists a positive edge, or there exists a negative edge. So this is 3 different types of relations. So this is a bit extension from of the classical graphs. So this concept actually was motivated by the social psychology problems, because you can naturally think of positive edges means positive relations between two vertices, and negative edges stands for negative relations. So this was the sign graph was introduced by Frank Harari in 1953 paper, and his motivations from these social networks. So natural questions you can ask. So given you a graph, how many signatures are there you can assign? So the answer is actually, of course, is 2 to the power of the number of edges, right? So let me take this very simple example with 3 vertices and 3 edges. You have this 3 cycle. So you can consider all possible signs. So it turns out that there are 8 possibilities. So you can further ask, are those structures are really different from each other. Of course, the answer depends on your purpose, right? On which properties you are concerned about. What I will explain that is for purpose, actually, there are only two different signed structures. So we can think about a very simple question or situation. You can think of a random walker stand at the vertices. You can think about the walker as an arrow, as I show here. So you think about this red arrow. He wants to travel around this cycle. At first, he stand at X, and at the next step, he jumped to Y. But because he travels through a positive edge, so they keep the direction of this arrow. So next step, he travel from Y to Z because he traveled through this negative edge, so I reverse the direction of the arrow. The next step is you travel from Z back to X, and because this is a positive edge, so I still keep the direction. So a natural question is, you travel around the cycle, you start from an arrow pointing to the pointing upward. Now you get an arrow pointing downward. So this actually reveals some structure given by this signature. So in geometry, this is quite natural because in geometry, this is called holonomy. So you travel around through a closed curve. It's a natural question. If you start from a tangent vector, will you come back to the same tangent vector? So when the space is curved, usually you will get a different tangent vector when you come back. So this is called holonomy. So here is a very simple model, very simple discrete model. You can think about the signatures as connections in Riemannian geometry, and this travel of this arrow you can consider as some parallel transportation if you are familiar with Riemannian geometry. But already you say that whether you come back to the original position or you come back to an opposite position makes really a difference. This is called balancedness by Frank Harari. So you can see whether you get back to the original position or not depends on the product of the three signs along the cycle, right? So we just take the product of all the signs along a cycle. For every cycle you always get a +1, Harari called the signature to be a balanced one. Of course, if you assign each edge to a +1, this is a trivial signature. It's always balanced, right? In this way, you can classify the 8 signatures on this simple example. So there are balanced signatures. The first 4 are all balanced. You can multiply these signatures. The others are all so-called anti-balanced. I will come back to this concept, but I should point out that it's not true that for every sign in the graph, either it's balanced or anti-balanced. There's something in between. But for this special example, it turns out that there are only 2 classes of signatures, balanced and anti-balanced. Okay. So there's another way to attack this balancedness is called switching. This is also a very simple operation. So you take a function defined on the vertices with values either +1 or -1. So that's like at each vertex, you have certain potential. And you try to multiply this 2 potential with this signature of the edge. Then you get a new signature. So the new signature is called switching equivalent with the original one. So we can also say we switch the original sigma by tau and get the sigma tau. There's a very important proposition that sigma is balanced if and only if you can find such a function tau such that your signature is switching equivalent to the trivial one. So this switching equivalent is actually an equivalent relation. So that means balanced signatures is actually the switching equivalent class of trivial signatures. So this tau for balanced signatures, you can actually easy to find this such a tau. Here I give an example, and again use this 3 cycle. Actually, you can get this tau, but here I use a W, this switching function by this random walker. I will not explain this in detail, but you see that switching is another way to characterize this balancedness. So we have a third way to detect balancedness. So let's reformulate a bit this switching operation. So for balanced signature, we know this, we can find a tau such that this multiplication equal plus 1. So if I reformulate a bit, we can say you can find a tau such that tau x equal to sigma x y tau y. Okay, so now I can, along each edge, I take the difference between tau x and sigma x y tau y, and I sum up around the vertex x and take some normalization. Also, I do a bit extension that I don't require this function to be tau again. I can allow this function f taking values, taking arbitrary real values. So now you get something like a Laplacian. You say that if the sigma is everywhere plus 1, this is simply the normalized graph Laplacian. But if sigma is non-trivial, this is sometimes called signed Laplacian, or in a more general setting called connection Laplacian, because this signature can be considered as some connection. Okay, so the third way to characterize balancedness is the following. You say if your sigma is balanced, that means you can find a function f. Actually, it's a very special one with taking values either plus 1 or minus 1, such that the Laplacian sigma tau equal to 0. That means balancedness means the Laplacian has 0 eigenvalue. In fact, you have even stronger characterization. You can list all the eigenvalue of this Laplacian. The first, you can say that the first eigenvalue equals to 0 if and only if the graph is the signed graph is balanced. And you also have another extreme characterization. The largest eigenvalue equals to 2 if and only if the signed graph is anti-balanced. But up to now, I still didn't explain what is anti-balanced. So we know balance means it is switching equivalent to trivial signatures. Anti-balance means it is switching equivalent to everywhere negative signatures. So it's another trivial one. So every edge you assign minus 1. So this is what anti-balanced means. So I'd like to point out a very important thing is the Laplacian is actually somehow switching invariant in the sense that the Laplacian of sigma tau and the Laplacian of sigma actually are similar. So you have this matrix transformation. So they share the same set of eigenvalues. In other words, the eigenvalues of Laplacian is switching invariants. I also want to point out that eigenfunctions are actually also switching invariant in some sense. That if f is the eigenfunction of Laplace sigma, then tau times f is the eigenfunctions of Laplace sigma tau. So this is also can be checked very easily. So this is so much I want to say about signed graph. Now I come back to the Nodal domain theorems. So the question is actually quite natural. So if we have an anti-function, we try to say there must be some zeros or non-zeros, but it can also happen every vertex has a function value non-zero. If we remove these zeros and see the remaining graph, the natural question is, are they connected? Or how many connected components are there? So for example, the graph Laplacian, we know the second eigenvalue corresponding to an eigenfunction which is vertical to the constant function. So it must have some vertices has positive sign, some vertices has negative function values. So you can naturally guess you remove the zeros, you will have 2 connected components. but is this really true for any for arbitrary graphs? So there's a book by Peter Stadler and collaborators about the Laplacian eigenvectors of graphs. They talking about like many things about nodal domain theorems. So maybe we first recall quickly the classical results in the continuous world. And the oldest result is due to Sturm. It's called Sturm oscillation theorem. This is just you consider one-dimensional space. So the zeros of the key eigenfunction of a vibrating string divide the strings into exact key subintervals. That means if you remove the zeros, you get key intervals. So this key coincides precisely with this index of the eigenvalue. There's a higher dimensional extensions due to Richard Cron. It's called nodal domain theorems nowadays. So if you consider higher dimensional cases, and of course the operator can be more general given any self-adjoint second order differential operator L, and in the higher dimensional, you again you want to remove the zeros. The zeros is called nodes by Cron, and you try to see how many subdomains do you get. Cron said you can get no more than k, smaller than or equal to k. In the higher dimensional case, you don't get the identity, the precisely k, but you know it cannot be more than k. So, so the subdomains is nowadays known as nodal domains, and the theorem is called nodal domain theorems. So a natural question is to ask, what are there any discrete analog? Unfortunately, you can easily find some counterexamples. This example of star graphs was pointed out, for example, in Friedman's paper in 1993. Here I give a very simple star graph. You have 5 vertices, and you can say you can calculate the eigenvalues of graph Laplacian is 0 because it's connected, 2 because it's bipartite, and there are 3, 1 eigenvalues. So in the talk of Zhang Dong, we know the multiplicity of 1 is related to the duplication of vertices. So here we have see this phenomenon again. So we know here I show this plus 1, minus 1, this give, and 0, this gives an eigenfunction actually, this corresponding to the eigenvalue 1. And if we remove the zeros, the central vertex, we got 4 connected components. So if the continuous nodal domain theorem is true, we should get no more than 2, right? But this stands for a counterexample for discrete version of nodal domain theorems. But there's ways to fix it. There's actually 3 possible ways. First possible way to fix it is you choose particular eigenvalues. For example, no, we say that lambda 2 is 1, but you see lambda 3 is also 1, lambda 4 is also 1, right? You can say this eigenfunction can also be considered as eigenfunction for lambda 4. So if this one is F4, so we get 4 connected components, then there's no contradiction. So that's good. That's a good case. So another thing is you try to choose possible particular eigenfunctions. So here's a trick. You choose eigenfunctions with minimal support. By minimal support, I mean that so you just compare the support of eigenfunctions corresponding to the same eigenvalue. But the minimal is not simply a minimal in size. It's actually minimal in the inclusion order. So if you have corresponding to the same eigenvalue as f, if you found another eigenfunction whose support is included in the support of f, if f has a minimal support, then this forces that the support of g has to be equal to support of f. So this is what the minimum mean. So if you found some eigenfunction with minimum support, you are always in good case. For example, here, corresponding to eigenvalue 1, you can use this eigenfunction. This eigenfunction has minimal support, actually, you can show. And you see, I remove zeros, then there are two connected components left. So this is again good because the eigenvalue index is 2. A third way to fix that is you including zeros. So here there's some concepts called weak node domains. Means you do not remove this zero, but you still keep that. You think about those vertices with non-negative values and those vertices with non-positive eigenvalues. So with the zero here, you can have two connected components actually, because this is a feature of this discrete space. So your function value do not necessarily change continuously from a positive value to a negative value, or it do not necessarily, if you change from positive value to negative value, it is not necessarily you have some zeros in between. So that's the feature of the discrete world. Okay, so it turns out with these 3 V's, you can really get a discrete version of nodal domain theorems. It was first established for the so-called generalized Laplacian, which is symmetric matrices with non-negative, non-positive off-diagonal entries. This includes graph Laplacian, but the graph Laplacian I explained in the beginning is not immediately fit into this setting, because that Laplacian, if you write out the matrix version, it is not symmetric, but it is similar to a symmetric matrices. So so in this sense, it also applies to the graph Laplacian. But this general Laplacian, you see, I don't have any requirement restriction about the diagonal entries. So that means you can your Laplacian can plus some potential terms. So also including some Schrödinger operator, or some Laplacian with some boundary conditions. For example, with Dirichlet boundary. This Dirichlet Laplacian can also be written as a Laplacian plus some potential terms. So this also covered by this generalized Laplacian. Anyway, this is a very general set of Laplacians. So so here says there's this is a work of Davies, Gladwell, Leydold, and Stadler. So in the discrete version, we should distinguish strong and weak nodal domains. For strong nodal domains, we just think about the connected components of vertices with positive values and the connected components of vertices with negative values. For weak, we replace positive by non-negative. We replace negative by non-positive. So that's the difference is that you including zeros in the weak nodal domains, as I showed in the previous example. Oh, okay, so here's the result. Their results goes for generalized Laplacian. You say for strong nodal domains, I use this curly S to stand for the number of strong nodal domains. The number of strong nodal domains is no greater than k plus r minus 1. So this actually is the first way to fix that. That you think about you plus this multiplicity r minus 1 means you think about the one with the largest possible index in the class of eigenvalues of the same eigenvalue, but it has multiplicity r. You think about the largest possible index, it works. Another way is you think about including zeros, you can show the weak nodal domains is actually no greater than k. As I said, we have a third ways you try to choose the particular eigenfunctions. This is some folklore results. If the eigenfunction f key has minimal support, then the number of strong nodal domains is no greater than k. So this is this one is we learned from the recent paper by Davies. Of course, for these results, there are many contributions in the history. The oldest results maybe can go back to Gentmark and Kahn in 1950s. They have some discrete analog of Sturm's oscillation theorems, and also goes back to 1970s. The works of Miroslav Fiedler. He actually shows for the second eigenfunction, the weak nodal domain is precisely true. There's also other contributors as Pors, Ross, Friedman, Colin Davadi, Van der Horst and Duer Heiners, I won't go to the details. There's in the book of Stadler, there's a very detailed historical review about these results. Okay, so now, as I said, our goal is try to go to arbitrary symmetric matrices. That means I want to remove this restriction about the off-diagonal entries. So why this is interesting? Well, I see there's many motivations for this generalization, but I just explain one here. So one of the motivation was explained in Gladwell and Xu in a 2002 paper. They commented that when one tried to use some finite element method approximation of differential equations, for example, Helmholtz equation, the discretization matrix will be a symmetric matrix, but the thing is that the signs of the off-diagonal entries of this matrix, although it's a discrete, it can be considered as a discretization of the Laplacian operator. It is the sign of the off-diagonals are not always non-positive. It depends on the characteristic of the mesh. So if the triangle for triangular mesh in the finite element method approximation, if all the triangles are acute angled, it is true that the off-diagonals entries are non-positive and M is a generalized Laplacian. But if some of the angles are obtuse, then you wouldn't get a generalized Laplacian matrix. You will get just an arbitrary symmetric matrix. So it's somehow essential to understand what happens to symmetric matrices if you want to understand this approximation process. So, but arbitrary symmetric matrices induce a signed graph. So here I give a simple example. If you consider such a symmetric matrices, and there's a signed graph, which can be considered as induced by this matrix. The rule is very simple. You say the diagonal term plays no rule. For the off-diagonal entries, if it is negative, you put a plus sign. So here's something I take I reverse the signature simply because I want to be compatible with the generalized graph Laplacian approach. Right, so because if we have a classical graph, we can consider every edge has a positive sign, so the corresponding entry in the generalized Laplacian is negative. So this is just incompatibility with there. Okay, so one can also easily calculate the eigenvalues and eigenfunctions of this example. For example, we take the second eigenfunction, F2, which I showed here. The red values is the function values of the second eigenfunction, and this is the induced signed graph. So the key is what is the nodal domains in this for eigenfunction of symmetric matrices, or you can ask what is the nodal domains of a signed graph. So here's a joint work with Chuanyuan, who is a PhD student at the moment at the USTC. He discovered this concept that for a signed graph and a function on this on the vertices, we consider those edges which we call strong nodal domain edges. The edges are those edges that you multiply the function values and the edge signs, you get a positive sign. For example, in this example, you multiply this -1 and this minus sign and this 1, you get a positive sign. So this edge is a strong nodal domain edge, which we denoted by E of S. So the strong nodal domain of a function f is simply the connected components of the subgraph induced by these edges E of S. And in this example, there's only one strong nodal domain, it's just these two vertices with this edge, right? but I have to point it out that this notion of nodal domain actually is switching invariant in some sense. That means the strong nodal domain of F and sigma actually coincides with that of tau F and sigma tau. If you still remember how the eigenfunction changes under switching, so if F is the eigenfunction corresponding to sigma, then tau F is eigenfunction corresponding to the switched signature sigma tau. Okay, but for the weak nodal domain is a bit subtle. Let me explain. It's not simply including zeros to the strong nodal domains. It's very subtle here. So we first define some W paths or weak nodal domain paths. That means in the path, you multiply function values and the H signs along the path. But if you have some function values 0, you don't multiply those things. So that means if you get some zeros, you just get rid of that, but you only multiply those non-zero function values. Okay, so if for some consecutive non-zeros xi and xj, you have this positive sign, then I call, if this holds for any consecutive non-zeros, we call it the W path. And for any non-zero vertices, this W path introduce an equivalent relations. Means X and Y are equivalent if either they are the same vertex or there exists a W path connecting them. And under this equivalent relation, you can find some the equivalent classes of those non-zero vertices. We call it Wi. So actually, this is what we will define as a weak nodal domain. But in order to keep compatible with the nodal domains of non-signed graphs, we do some a beta extension. So if there's a W path from a vertex to some vertices of Wi, we will add this vertex X to this Wi, and then we get a Wi0. Actually, this step is just you including some zeros around this Wi. Weak nodal domains, this concept is again switching invariant. I still take this example. For this example, actually, we see already these two vertices with this negative edge is a strong nodal domain. So the weak nodal domain for this example is simply you include all those zeros. Because for those zeros, you say from 0 to this -1, this is a W path because there are no consecutive non-zeros. So this may be a bit trivial, but if we change this minus sign to be plus sign, we say that this 1 and -1 are not connected by a strong nodal domain path anymore, but it is connected by a weak nodal domain path. You just simply travel from -1 to 0 and to 1. You multiply -1 and the minus sign, but 0 you get rid of that. Multiply with plus and multiply with 1, you get a positive sign. So this is a weak nodal domain path. So then with the extension, you see the whole graph is actually still has only one weak nodal domain. Okay, so let's come back to the original example here. I give a full list of the strong nodal domain and weak nodal domains. You see there are some differences. Probably I won't go to the details here. Okay, now let me come back to the the results. The results with Chuanyuan Ge is the following ones. If you compare this one with the result of Peter Stadler and collaborators, you see there's in principle no differences. The only thing is that I removed the restrictions on the off diagonals. But of course, those concept of nodal domains the key is to find the right concept. So what our result is that for arbitrary symmetric matrices of a connected signed graph, you have the strong nodal domain is no greater than k plus r minus 1. The weak nodal domain is no greater than k. If you think about eigenfunctions with minimum support, you get this number of strong nodal domains no greater than k. Okay, so that's at least an evidence that our concepts are the correct ones. I have to mention that in principle, the first estimate this K plus R minus 1 was has already been obtained by Ali Mohammedin, who is now working in Anhui University in 2016. But he uses different notations, but it's somehow equivalent to this first eigenvalue. Another thing I want to point out is that if the induced standard graph of the symmetric matrix is balanced, then our result is just simply reduced to Davies, Gladwell, Leydold, Stadler's result. So this is very consistent with existing results. But in the remaining time, I want to explain that this is actually quite useful to understand some existing results and get more, sometimes it gives more deeper results. Maybe I start with, okay. So I have another slide to briefly explain the idea of the proof. Actually, the key of the proof of either a continuous nodal domain theorem or discrete nodal domain theorems lies in something called the unique continuation property. So here, with our concept of weak nodal domains, although you say that it's very subtle nodal domains, but it has very good properties, as we have a discrete unique continuation theorem in the following sense. So you think about an eigenfunction f of an arbitrary symmetric matrix M and a corresponding eigenvalue lambda. And you denote all the weak nodal domains by di's. And you restrict your eigenfunction f to each di and extend it by zeros. You get a set of functions gi. So the result set says the following. So I assume connectedness of the graph. So you think about any linear combination of those gi's and defined by g, denoted by g. We say that if you say you find some coefficients ai such that g is an eigenfunction of m corresponding to lambda, then it must hold that all the coefficients should equal to each other. In another word, so if you restrict to this set of functions, and if some of them is an eigenfunction corresponding to the same eigenvalue as the function f, and if this function coincides with this function f in a domain di, in one domain, then it coincides with f everywhere. So this is some kind of discrete unique continuation theorem. So this is a key to the proofs. So much for the proofs, and I want to explain that this results together with this balancedness and switching, the concept of balancedness and switching operations of standard graphs can lead to very interesting views, different views of the existing results. The first example is some results due to Roth. Let me probably first explain some earlier results before Roth. So first is a classical Penrose-Frobenius theorem. This theorem said for any real symmetric irreducible means the induced graph is connected, and entrices non-negative matrix. And we denote by rho of A the spectral radius. The Penrose-Frobenius tells us that the spectral radius of a symmetric irreducible entrices non-negative matrix is always an eigenvalue, and actually is a simple eigenvalue. And the corresponding eigenfunction can be taken to be everywhere positive or everywhere negative. There are no zeros of the eigenfunction. This is what Penrose-Frobenius told us. So a consequence of this classical Penrose-Frobenius theorem in the current setting can be stated as the follows. That is, for a graph, if it's connected and the M is a generalized Laplacian, then the smallest eigenvalue of the generalized Laplacian is simple, and the strong and weak nodal domains of the corresponding eigenfunction equal to 1. So this is simply an application of Penrose-Frobenius theorem, because we know the minus m actually have non-negative off-diagonal entries. You can you can modify by an identity matrix to make sure all the diagonal entries are non-negative. Then you can apply Frobenius theorem. And you can also take large enough C to make sure that the spectral is actually minus lambda 1, right? It's actually lambda 1, right? So then this, so the simpleness follows from parent Frobenius, and this number of strong nodal domains is just simply because the eigenvector or eigenfunction have the same sign. So there's only one connected component. Okay, this is a very simple application. So in 1989, Ross in the paper gets the following result. He said we can have similar phenomena for the largest eigenvalue of Laplacian, but it needs to require the graph to be bipartite. He said if for a connected bipartite graph and M is the generalized Laplacian and lambda n is the largest eigenvalue with eigenfunction Fn, he gets lambda n is simple and the weak and the strong nodal domain of Fn is actually attains the largest possible value, which is n, the size of the vertices. I mean, in spirit, this looks very much like the previous result, but requires bipartiteness. What I would explain next is in our new results, we can give a brand new point of view of results, and you can see this is again a simple consequence of the Penrose-Frobenius theorem. For the key is to realize that for a bipartite graph, so the normal graph you can consider each edge has a positive sign. So this graph is actually anti-balanced because we know in the bipartite graph you only have even cycles, right? So the edges can be just in between two subsets, and you just put the switching function in one set plus one, the other side minus one. Then you switch every edge to be minus. That means this signature, this trivial signature on a bipartite graph is actually switching equivalent to all negative signs. In another word, on a bipartite graph, the trivial signature is either balanced, is both balanced and anti-balanced. So this is a very special property of a bipartite graph. Okay, so that means because the nodal domains with our new concept is switching invariant, so it makes no difference if we consider all everywhere negative signs. So then this changes the things very interestingly, because now the generalized Laplacian, the corresponding Laplacian, the corresponding matrix M to the everywhere negative sign is the non-negative, have everywhere non-negative off diagonals. Again, we use the trick with plus the C times identity. You can see that you can make the corresponding matrix to be a non-negative matrix, and you apply parent Frobenius. And in this time, the largest eigenvalue is the spectral radius, and it is simple, and the corresponding eigenfunction is everywhere positive. But you remember the eigenfunction, the function value is everywhere positive, but the edge sign is negative. So each edge, you multiply eigenfunction values and the edge sign, you got the negative sign. That means each edge everywhere, and no edge is strongly a nodal domain path or weak nodal domain path. That means each vertex itself is a strong nodal domain or weak nodal domain. So you get the number is precisely the size of n. So in this view, just using switching invariance, you can easily see that this Ross result is also a consequence of parent Frobenius. So let me show another example. Sorry, I can mention that these Ross results can be extended to this generality if the gamma is a connected sign graph, and for some compatible matrix, you can show that it's the signature structure is anti-balanced if and only if the weak nodal domain and strong nodal domain, the number equal to n. And in this case, lambda n is simple. So this is just a simple extension. So in the remaining time, I want to show another case that this switching invariance and this new concept of nodal domains on signed graph is quite useful to understand existing results. This is the result of Fiedler. So we know Fiedler has very famous results about algebraic connectivity. Nowadays also known as Cheeger constants in 1970s. Actually, in 1970s, he has 3 papers published in Czech Math Journal. The first one in 1973, he introduced this algebraic connectivity. Is actually the second eigenvalue, right? So it's related to the Cheeger-Cart problem constants. And a third paper is also somehow known very well to people as is with a long title. In this paper, actually, he showed this weak nodal domain equal to 2, if in the terminology of nodal domains. In our opinion, there's the third paper called Eigenvectors of Acyclic Matrices, although there are some citations and also some further discussions, but maybe this paper among the 3 papers is the most somehow attracts the less attentions than the other 2 papers. But we want to say, using our terminology, we can reformulate the results in this paper and get very, very interesting thing. Let me first explain what is the acyclic matrices. It is a symmetric matrices whose induced graphs contains no cycles. So that means the induced graph are trees or forests. So in principle, what Fiedler do here is consider some matrices associated to trees or forests in this paper. He get a very interesting result, but with a very long statement. So I copied from his paper here. You see it's already occupied 2 slides here. Maybe let me quickly explain, maybe not too detailed. So he consider a cyclic matrix and consider a particular eigenvalue lambda, and he used omega plus, omega minus, and omega 0 to indicate the position of this eigenvalue. Because omega plus is count how many eigenvalues is greater than it, and omega minus is how many eigenvalues smaller than it, and omega 0 is simply the multiplicity. So you first see that these are related to the indices of the eigenvalues. Okay, so under some conditions, they assume there's no isolated 0 eigenvalues. He gets a precise a description of these positions. This is related to the index. And but it involves some number called a plus, a minus. What is a plus, a minus? A plus, a minus is related to those edges with such a property. Maybe you can recognize this already. This appears in our concept of strong nodal domains, because here you just multiply the function values. Here the function is y, and the matrix entries. So this appears in the strong nodal domains concept. So this at least give you a feeling this is closely related to our results. If there are isolated 0 coordinates, they have some even more complicated things, and you delete those indices and get new matrices. I will not explain anything more here, but I want to see we can reformulate in our terminology in a very simple way. So first observation is that on the tree or forest, any sign is balanced. Why? Because for a tree or forest, there are no cycles. But balancedness are related to the cycles, because a signature is balanced if and only if for any cycle you multiply all the edge signs, you get +1. But if there are no cycle, so there are no restrictions. Any sign on tree or forest is balanced. So that's the first observation. And those are related to multiplicity and positions, and A plus are related to the E of S, the strong nodal domain edges, as I said. So here's the reformulation of Fiedler's result. So you think about a cyclic matrix And we know the induced signed graph is actually a tree with a signature. But as I just said, any signature on the tree or forest is trivial. So it's switching equivalent to the trivial signature. So if you list all the eigenvalues as follows, and you denote those Fiedler called isolated zeros. So let me explain a bit. So what is the isolated zeros of a function f? So it is just a set of vertices which are zeros of the function fk. Moreover, you require all its neighbors is zeros again. So he called it isolated zeros. Maybe it's a bit confused for some people, at least for me at the first time. So this isolated means this zero is surrounded by zeros. It's not surrounded by non-zeros. So, in our new terminology, we can reformulate the Fiedler's results in the following way. So it simplifies the number of strong nodal domains in our sense of fk is no greater than k plus r minus 1, and the lower bound is k plus r minus 1 minus capital F, the size of capital F. So I have to admit that in some sense, I didn't get a precise reformulation of the results because you see in Fiedler's results, you get identities. But we can do that. That will make the theorem a bit longer, but I omit the precise reformulation here. But this is already enough for us to understand what Fiedler did here. He actually did for signed trees, the strong nodal domain theorems. And moreover, he get a very good lower bound. Why I said this is a very good one, I will explain. So in the continuous world in high dimensional case, we know the nodal domain, there are no trivial nodal non-trivial lower bound for number of nodal domains. So we know by Sturm's results for the one-dimensional case, you get precise identities, or in other words, you get meaningful upper bound and lower bound. But when the dimension is greater than 2, you wouldn't have good lower bound anymore. But in the discrete world, that is in the 2008 work of Berkolaiko, he realized that for discrete cases, you do have a non-trivial lower bound because you can think about like trees. Trees can be think about as branching one-dimensional spaces. So here, there's some chance to get some lower bound. So just compare based on understanding about tree graph. So here's what he showed. He showed if the induced graph of generalized Laplacian is connected and the case eigenvalue is simple and the corresponding eigenfunction has no zero, although these are very strong restrictions, then he gets nodal domain theorem tells the number of strong nodal domains no greater than k, but the non-trivial thing is this is lower bound. He said this is the lower bound is k minus Lg. Lg is the number of cycles in the graph. So for tree graph, we don't have cycles, so L just equal to 0. So that means for trees, if you have this simple multiplicity 1 and non-zeros, no zeros, you get identities. So this is a Berkolaiko's observation, and this was further extended by Professor Xu-Yau and Chuanyuan Ge in 2012. They said if you allow arbitrary multiplicity and allow zeros, you just modify the lower bound by k plus r minus 1 minus cycles, number of cycles, and minus number of zeros. So this is their result. But if you compare with Fiedler's result, at least for trees case, of course, in this case, the number of cycles is zero. But you say Fiedler did not need to minus all the total number of zeros. It just minus the number of a part of zeros. So a special set of zeros, we call it Fiedler zero set later. So that means if you think about Fiedler's results in the correct way, or in our terminology, actually Fiedler gets in the case of tree graphs a better lower bound than Xu and Yau. So it turns out this can be a generally improved Chuanyuan's lower bound. So let me explain some concepts very quickly. So in a graph, we call a vertex tree-like. If you after removing this vertex, you will increase the number of connected components by the degree -1. Of course, this happens for vertices in a tree. So if it has this property, we call it tree-like. The second thing is we call Fiedler zero site. What does that mean? It means a vertex which is a zero. First, it is a zero for a function where or function f, and one of the following two properties holds: either all the neighbors are zero, or the vertex is not tree-like. So you say that if the graph is a forest, so our set of Fiedler zero sets is coincide with Fiedler's set of isolated zeros, right? So this is a natural extension. So our results set we have this lower bound estimates. So we can improve Chuanyuan's lower bound. So you do not need the total number of zeros. You just need a part of the number of part of the zeros. Of course, the results also on the one side improves the previous results. On the other side, is also generalizes the previous results to arbitrary symmetric matrices. Okay, so maybe I should stop here. So this is our papers already on arXiv this year, and maybe in the last, let me mention this month is already appear a new arXiv paper by Zhang Lei and Hou Yaoping, Professor Yaoping Hou from Hunan Normal University. They extend our concept to they called Stein hypergraphs. It seems also quite useful there. So thank you. So I would stop here, and I'm open for any questions or comments.